Hi everybody, this is Manuel, also known as Mitsuta. In this tutorial we will have a look on how to create a dissolving animation using VDBs and the Solver node. As always, you can find the file in the description for free. This channel can only move on with your support, so please like and subscribe, it really makes a difference. Thanks also to Flavia Mazzanti for this tutorial's coffee. Check out her great work, where I have also been part of. So, let's get ready! So, back in Houdini, drop down a geonode. And as first step, we import our geometry with a file node. What we try to do for this animation is basically scaling spheres inside our geometry and to subtract them from it. We start by converting the mesh into a VDB. Use here a VDB from Polygons node. VDBs can be basically understood as a volumetric data in form of a grid. Instead of a mesh with faces and vertices, we deal with voxels. Voxels can be imagined as cubes or cells in a three-dimensional grid, which store data describing the shape of our geometry. Operating on this logic, it allows us to create extreme distortions and complex operations on geometry, which would be not possible on actual mesh. In the parameters, we define the resolution of the voxels here in the voxel size. For me, a small value like 0.01 works fine. Make sure to create a distance VDB, and the voxel band values define the size of the grid. We can select here Fill Interior and set the exterior band to 5. In order to spawn subtracting spheres inside this volume, we need to convert it into points, which will work as their centers. Using the points from volume node, we can scatter them inside our geometry. We can make the scattering a bit more random by increasing the jitter scale. And increase the number of points to something like this. We are now going to specify the initial points from where the dissolving process should start. We name our group Source and set the group type to Points. Next, we select the points directly in the viewport through the selection mode. For this, I like to use the lasso selection tool, which is much more handy than the rectangular one. If you have your selection ready, hit Enter to confirm. Before we start creating the animation, we need to add to these initial points some parameters. Herefore, drop down an attribute create node. Here we select our group and we are adding a p-scale attribute. As constant value, use 0.03. This attribute is defining the scale of the subtracting spheres. We can also visualize it fast by scattering some spheres on the points. You see here that when we change the p-scale value, we also change the scale of the spheres. We move on by adding another attribute create node. Here we want to add an ID attribute, which corresponds to the point number of each point. Down here, instead of adding a constant numeric value, we'll link another attribute, type @ptnum, which is the attribute for the point number. To know more about common Houdini attributes, you can look them up here in the documentation. I will post a link in the description. So, for the next step, it's very useful to visualize the source points. We can simply use a color node for this. Here we can select the group and pick a color. Now we start creating the animation, where the selection of our group increases by its neighboring points. We are going to create this process by writing a small vex code in a wrangle node. The first step is to look if a point is in the source group, and if so, it should find the closest neighboring ones and add them to the group. We start by typing if and in brackets add group underscore source equals to 1. And then in the curly brackets we type near points, which is the function we need to find the neighboring ones. Follow this by 2 brackets and a semicolon. When we select the function and hit F1, we open directly Houdini's documentation, which is telling us more about the function itself and how to construct it. We see that the function creates an array of integers, symbolized by the square brackets. This array will contain the point number of the new found points. We type int for integer, and then the variable name is pts, followed by square brackets and equals the function. Now inside the brackets of our function, we start by specifying the geometry input for the points we are looking for. In our case, these are all the points except the source ones. For this we are going to create a second input into the wrangle node with only the non-source points. But for now we finish the function and create this input later. For the second input, we use the index 1. Next, we declare the position from where to start looking from, which is the actual point's position stored as attribute p. As search radius we take 1, and we want to select only one new point for each of our source points. Also, don't forget the semicolon at the end. Now we create a second input for the wrangle node, containing the non-source points. Use herefore a delete node. Select the group and delete selected from the entity points. As next, we use a for each loop to run through each value in our array. Remember, the array is storing the point number of the new founded points. Type for each, and in brackets we define first the variable representing the value in our array. In our case, it is an integer, and then name it pnum, followed by a semicolon, and pts is the array to go through. Open and close the curly brackets, and now we want to extend the source group by the new selected ones. Therefore, we use the setPointGroup function. We use the first input as our points to change, and the group is called source. Now we need to define the point number. But now we have a problem. We have a point number from the nearest point, but points from the first and the second input have different point numbers. This is because in the second input we have a reduced amount of points, which causes a change in the point number assignment. Here the ID attribute solves the problem, as it will correspond between the points from both inputs. Also, if you're not familiar with visualizers and you want to know how this one has been created, have a look at my other video about visualizers. I put the link down in the description. Back in our code, we can get the ID value from the corresponding point with the point function. In the brackets, we start again by specifying the input, which in our case is a second one and has the ID number 1. The attribute we need is called ID, and the point number is the one stored in the array, which we gave the variable name pnum. Finish now the setPointGroup function with 1 for the group value and type set. Don't forget the semicolon at the end and hit Ctrl Enter. Comparing now both with the color node, we see that we increase the selection by 1 iteration. Perfect. Not only the selection, but also its p-scale value should change with every iteration. Back in the wrangle node, we add a setPointAttribute function. The input is 0 and the attribute is p-scale. For the point number, we need again the ID attribute. To keep a cleaner code, I prefer to create our own integer variable named ID and to use that instead of copying the point code all the time. As p-scale value for each new found point, I want a random value. Type rand, and in brackets, we need a unique seed value. Here the pnum variable works fine. The random function creates values from 0 to 1, but I want the number to be very small, so I'm going to divide it by 10. Finish the function again with set and hit Ctrl Enter. Also, the p-scale from the previous points should increase by each iteration. At the beginning of the if loop, we type add p-scale times equals 1.05. Perfect. This is now the process for one iteration. In order to get an animation, we would need to repeat this operation over time. To do this, we need a solver node. This node takes the input of the previous frame and uses it as a new input to iterate over and creating therefore a loop. We take the delete and the wrangle node, connect the solver and paste them inside. We also add an out node to specify the output of the solver. Let's go back up and have a look at the animation with some spheres. This looks good, but we need to add another rule that the p-scale is not exceeding a certain threshold. Here in the code, write a if function stating that if the p-scale value is bigger than, let's say 0.5, and in the curly brackets, that p-scale should then be equal to 0.5. Perfect. We can also add a small randomness to the selection of the points. Inside the for each loop, we create another if function, where we say that it should only execute a code if a random generated value between 0 and 1 is bigger than something small, like for example 0.3. As seed, I used again the pnum variable, and I also multiply it by the actual frame, defined by the add frame attribute. Going out, we can see the difference. As last layer, I want also to make the scaling of the spheres more irregular. Therefore, we could create an initial noise attribute, which we're going to use instead of the constant 1.05 p-scale multiplier in the solver. I prefer to use a point warp node as I can directly visualize the noise field easily. Here we add an anti-alias flow noise, and as input we use the position attribute p. When you plug in the result in the CD value, we see that the color changes. CD corresponds to the color attribute in Houdini. Also change the frequency to get a smaller pattern. We can now export this float value as a new attribute. Drop and connect a bind export node. And here, make sure it is set to float. And we name it noise. Looking in the geometry spreadsheet, we can see that the attribute ranges from minus 0.03 to plus 0.37. For the p-scale attribute, we want to have only values in a certain range. To resample this range, we connect it to a fit node. We type in minus 0.34 and 0.37. And now as destination, we can try something from 1 to 1.06. We can imagine this value now as the new p-scale multiplier for each iteration. We also don't need the color visualization anymore, and we can disconnect it. Going now back in the solver, we execute this plan and replace the 1.05 multiplier with the new noise attribute. Let's go out and check it again. So far this looks good to me. Of course you can always go back and change the values to create a stronger diversity or more variation into the pattern. This concludes now the animation for the subtracting spheres, and we are going to import also the VDB geometry from the beginning in the solver. Combine both inputs in a merge node. And in order to separate both elements again inside the solver, we put all the points into a group. Give it a name, and the group type is points. Now back in the solver, we use a split node to separate the VDB and the points again. The group is the points. And now reconnect the points back into our previous system, and for the VDB we create a null node to keep the network clean. In order to subtract now spheres from the VDB, we need to convert these points to VDB spheres. Therefore, use a VDB from particle node. Make sure to have distance VDB selected and change the voxel size and the point radius scale parameters accordingly. Now we can subtract these spheres from the actual geometry with a VDB Combine node. Connect both VDBs and inside here choose this operation SDF Difference. We want to make sure that also the points will be outputted together with the VDB for the next iteration. Let's dive out and add again a split node, together with two null nodes to split the points from the VDBs. So let's have a look how the animation looks so far. Perfect. We can also smoothen the shape for a better look. Use therefore a VDB Smooth node. And here we can change the type and the strength. Further, it is also possible for us to smoothen only the areas where the spheres intersect and leave the rest sharp. We see here in the Smooth node the second input. This one allows us to apply a VDB mask. This input demands a fog VDB. Simply copy the VDB from particle node and change here from surface to fog. You can see the result, and by playing with the radius scale, we can change the affection. Now the result looks much better. Here it's also good to set the lower resolution matching the higher one to have a more detailed result. As next, we are going to add some additional details in form of particles floating out of the geometry while it's dissolving. I would also love to see your results. Tag me on social media and I'm really happy to share your artwork. If you haven't, give this video a thumbs up, it really helps a lot. And let's move on. By using a pop network, we will emit particles from the points in our source group. Plug in the points in the first input and dive in. The pop network allows us to emit particles and drive their behavior by applying forces. We begin by defining the source of our particles in the pop source node. Go to the source tab and choose our source group. For the emission type, select points. Now in the birth tab, we define the amount and frequency of the emission and also the lifespan. Here choose impulse activation, which emits the defined amount of particles each frame, and set the constant activation to 0. As impulse count, 5 works fine for me. Defining the lifespan of the particles, we can say that once it's emitted, it should exist around 5 seconds. So now disable the guide geometry and hit play. We see that the points are scattered, but we need to add an upward force to make them fly away. We use a pop force node, where inside we add a small force in the y direction. You can also add some auto turbulence here, depending on the look you want to achieve. But for this animation, I keep only the upward force. Dive out and let's have a look together with some spheres. We see immediately that the spheres become too big and don't look so good. To fix this, we are going to delete the ones with the p-scale over a certain threshold. Inside the pop network, we can add a pop kill node. By enabling the vex code, we can make a simple if function, saying that if the p-scale exceeds a certain value, the particle should be deleted. Type if, and in brackets, add p-scale bigger than, let's say 0.2. Then in the curly brackets, that equals 1. Don't forget the semicolon, and now let's see the result. Much better now. As next layer, we will make the spheres also dissolve or vanish by shrinking them over time. For this, we can use a point warp node, but of course you can also do it in a wrangle node if you prefer. Our goal is to create a multiplier, which is at the beginning 1 and later goes towards 0. For this, we are going to divide the actual age by its life. And because it will give us now values from 0 to 1, depending on the age, we need to remap it to 1 and 0. This time we use a ramp node and choose as type the spline ramp. The ramp will be automatically displayed outside on the VOP node. For now, let's create a spline like this. The ramp works in the way that the input values are along the x-axis and the output values are the corresponding y values on the spline. In order to set the ramp more precisely, we need first to see the changes on the actual spheres. Import the p-scale attribute with the bind node. Here choose float and type in p-scale. Now multiply it and then use a bind export node to export the p-scale attribute again. Now as we see, we can go out and adjust the ramp better. Also the interpolation can be changed. If you use B-spline for example, it creates a smoother transition. Something like this looks good to me. As last step, we combine both the spheres and the geometry back together. Here again convert the particles into VDB spheres with a VDB from particles node. We can use similar values as previously, and for me these ones work fine. The approach from here is almost the same as from the solver node. Combine both VDBs together with a VDB Combine node, and here choose SDF Union. This is now the moment where I go back and adapt some settings. First I go back in the solver node. In here I make the sphere smaller. Also I change the related smooth mask. Therefore we can get a more detailed and slower dissolving process. Now I also tweak a bit the ramp to adjust the size of the emitting particles. This is the power of procedural animation. You can at any time make changes throughout the whole script. This is now much better. Also repeat the process with the VDB Smooth node, combined with a VDB mask from the particles. You can play around with the point radius and the smooth values to find a good balance. Seeing the result, we realized that we lost a lot of details from the points in the process. I also re-added the VDB spheres back with a VDB Combine node. But before, I shrink them a little bit to not cover the smooth transition we just created. The process. For this, you can try the VDB reshape node. This allows you to dilate or erode the VDB. Play around with the setting till you find a good balance for you. And this looks good. Perfect. I hope this tutorial was useful for you and to see you in the next one. Ciao!